I'm happy to welcome Smita Sahu from Durham University, and she's going to speak about high-order filter schemes for time-dependent first-order Hamilton-Jacobi equations.
Yeah, thank you, Stefan. Thank you for all of you to be here in this summer vacation, and thank you, Stefan, for inviting me. So I'm going to talk about the filter scheme for time-dependent first-order Hamilton-Jacobi equation. So this is the joint work with Olivier Bokanowski from Paris-7 and my PhD supervisor Maurizio Falcone from La Sapienza, University of Rome. So this is the work when I visited Olivier during my PhD for some months. Oh, sorry. Okay, sorry for that. Okay, so here is the outline of my talk. So I will introduce the model problem, which kind of Hamilton-Jacobi I am interested in. Then I will also show you the definition of viscosity solution. Then I will introduce the filter scheme and what ingredients I need to define the filter scheme, and convergence results for the filter scheme, and some numerical difficulty, and then I will show you some numerical evidence, and I conclude my talk with the future direction. So let's start. So I am interested in this kind of Hamilton-Jacobi equation. So this is first order time dependent Hamilton-Jacobi equation. So for these kind of equations, there is no classical solution exists because the lack of smoothness. Even though if you start with the smooth data, but after some time solution is not smooth anymore. So then the notion of viscosity solution has been introduced by Crandall and Lyons. And so under these assumptions, so if initial data is ellipsis continuous and Hamiltonian satisfies these two properties, then this equation has unique viscosity solution. So yeah, so now, so it's just if you are not familiar with the notion of viscosity solution, so for those kind of equation we write weak solution in viscosity sense. So if V is a bounded, it's bounded and uniformly continuous, and it's called viscosity solution if and only if for any test function if two properties holds. So if for every point on the domain V minus phi have local maximum, then it's called viscosity subsolution. When it has local minimum, it's called viscosity supersolution. So we have this weak notion of viscosity solution, and this makes numerics hard to develop the numerical schemes for such kind of equations. There are some available works for the low order scheme, but very few for the high order scheme. So let's see what we have in literature. So the first work for this kind of Hamilton-Jacobi equation introduced by Crandall and Lyons, 1984. So this work inspired by the fact that in one dimension Hamilton-Jacobi equation, the solution of that equation is the primitive of solution of hyperbolic conservation law. So due to this fact, people were able to develop some theory and numerics. So here Crandall and Lyons, they introduced some monotone schemes with the convergence results. So this is the only paper where we have error estimate for any kind of a scheme for Hamilton-Jacobi equation. Okay, and then there are some work by Sapienza where they solve some different kind of Hamilton-Jacobi like front propagation problem, and then there are some high order scheme. So it's called ENO scheme, essentially non-oscillatory schemes. They are high order numerically, but there is no stability or convergence results theoretically. And then there are also some central difference scheme, and then there is this semi-Lagrangian scheme which is not fully Lagrangian, which is like coupling of ODE methods with interpolation technique. So it's introduced by Cappuccio del Citta, and then Falcone, Ferretti, Carillini, they have those scheme for different kind of Hamilton-Jacobi, and they do have the convergence results here. And then there are some discontinuous Galerkin approach, and this also inspired by hyperbolic conservation law by Cockburn, and then it's extended to Hamilton-Jacobi equation. So, but in these kind of method, they have stability issues. For instance, this work by Bokanowski and others, they have coupling of semi-Lagrangian with discontinuous Galerkin method, but there is the stability issues. Then there are some finite volume method, and for example, these all schemes are implicit schemes, and they design for the non-structured mesh, and which makes difficult to implement such kind of schemes. Okay, so my goal is here to develop a nice simple version of the high order scheme for solving Hamilton-Jacobi equation, and then try to prove the consistency, stability and convergence for the scheme. Okay, so Goodnam theorem says that if your scheme is monotone, then it can be at most first order. So if you want something higher order, you have to look for the something else, non-monotonicity, and that makes the convergence part difficult. It's hard to combine non-monotonicity with the convergence to the viscosity solution. So this is the core of work, and by Bals and Suganadis, they presented this theory that epsilon monotone scheme are convergence. So what we want to stay in those convergence criteria. So for example, Froses and Obermann, they give the filter scheme for some second order PDEs, stationary second order PDEs. So here I focus on evolutive first order time dependent PDEs. Okay, so now we need these few ingredients for the filter scheme. So for a monotone scheme, I will represent by SM, and for high order scheme, I will call it A with arbitrary order, and then I need a filter function. So these three are the key ingredient which I need to design the filter scheme, and I will go through each of them. So okay, so for this setting we can do everything in higher dimension, but for the simplicity I am setting everything in 1D. So I have delta t time step for the time axis and delta x for the space axis. So I discretize everything uniformly, and then so that's how I denote the monotone scheme. For monotone scheme, I always follow the work of Crandall and Lyons. So in monotone scheme, this is my numerical Hamiltonian, and which is like these d plus and d minus are left and right derivative, and so for monotone scheme, the numerical Hamiltonian is ellipsis continuous, it satisfies consistency property, and it's monotone. And of course here we have CFL criteria, so these scheme must satisfy the CFL criteria. So that's what Crandall and Lyons gave for the monotone scheme. Okay, so if in the scheme, if the solution is C2, then we can replace it by this smooth function, and we can use the Taylor's expansion, and then we can derive the consistency error estimate. So this can be obtained only by using the Taylor expansion. So for the monotone scheme, Crandall and Lyons, they gave this error estimate. So here if the scheme is monotone, this one what I presented here, and V is the exact solution at xn and Tn and xi's, and H satisfies, H is ellipsis continuous in all the variable, and initial data is ellipsis continuous, and then we can obtain this error estimate. So that's the error estimate only we have for Hamilton-Jacobi equation. Okay. Okay, so now I will go to the high order scheme. So high order scheme, its derivative you discretize according to choice of your order. So for instance, I can have the central finite difference scheme. So we know central finite difference scheme is unstable for those kind of equation, whatever CFL you choose. And so I denote the scheme like that, and for these schemes, high order Hamiltonian is ellipsis continuous, and similarly if we have we choose the smooth function smooth enough and we substitute here, and then we can derive the consistency error estimate for the high order scheme. And these schemes are unstable, they are not stable at all. Okay, so but of course we can write down the consistency error estimate. Okay, so now I have everything to write down the filter scheme. So filter scheme I am denoting by SF, and so we have this monotone part plus epsilon delta t times this f, I call it filter function, you will see what it is, and then this difference with high order and monotone scheme divided by this factor. So this epsilon is a switching parameter. So idea is when your solution is smooth, the scheme should choose the high order scheme, and when your solution is less smooth, less regular, it switches to monotone scheme. And so it's like monotone plus epsilon thing. So you never going to be blow up. Your scheme is going to be stable. At least it will obtain the monotone part. And of course this epsilon plays very important role. You will see in few slides how we choose this epsilon. So that's the simple construction of the scheme. Okay, and okay, so the filter function we use is this filter function. So if you see here, so okay, so if x is less than or equal to 1, then it chooses x, otherwise it's 0. So here if this is 0, then we are using monotone part, and if this is 1, this quantity is less than or equal to 1, then this will cancel out and SM cancel out, then you will be using high order part. So the scheme will you need this to stay in the high order scheme, and otherwise you have filter function 0 and gives you the monotone scheme. And on the paper of Froses and Obermann, they solved the stationary equation. So that filter function was different, and that filter function is not working here. So we use this filter function. Okay, so for the filter scheme also, because we have monotone scheme plus that combination, so if we choose V smooth enough, and then we can use the Taylor expansion and we can derive the consistency error estimate for the scheme. So because the filter function is always going to be bounded by 1, because it's bounded by 1, whatever you put inside, it's always bounded by 1. So you will end up with this kind of consistency error estimate. So this directly implies the scheme is epsilon monotone. So we fulfill the criteria of Barlin-Suganadis theory. So this epsilon monotone scheme, this scheme converges towards the viscosity solution. That's nice. Okay. Then so we able to prove some error estimate for that. So if A1 A2 means if Hamiltonian satisfies the basic properties, ellipsis continuity, and initial data is also bounded and ellipsis continuous, and SM is a monotone scheme with monotone Hamiltonian consistent and ellipsis continuous, and we denote UN by filter scheme. So UN solution is coming by filter scheme, and then we have bounded filter function by 1, and so this is the exact solution at t and xj point. So the first thing, if we choose our switching parameter in this way, less than some constant time half power of a step size, then we can obtain the Crandall and Leon error estimate, and that's nice, we can obtain this estimate, but we also want to improve it. So if the solution is C2, then we choose epsilon instead of a square root of delta x. If we choose this is power 1, then we can have the power 1 in the error estimate. Okay. And then the third point, the scheme is locally high order. So if we chose epsilon in such way, then the filter scheme is going to be the same as high order scheme, and then the error estimate for the filter scheme is the same as the high order estimate. Then the scheme is locally high order. So I will give you the brief of these proof, then it will be more clear. So we will start from this one. So just to be note that UN is the scheme calculated by filter scheme, Vn is the exact solution. Okay. So and then I denote Wn plus 1j for the monotone scheme. So what I am doing here, I have this Ujn plus 1, and this is the exact solution. Then I add and subtract Wjn plus 1. Then I am just taking this first part here, and then I can write down this as a filter scheme. So that is Sm plus epsilon delta Tf. So now this thing is dominating all monotone part, and then we have this epsilon thing. If I take the absolute value and the maximum, and then this will give me this because of monotone property of the scheme. And then here I have, because the filter function bounded by 1, so it will give me 1 here. So now if I do the recursion, I go to n minus 1 and so on. So this term will give me epsilon times n delta t, and n delta t becomes capital T, the total time, and epsilon. So we are done with this part. But if you look at this part, this is the exact solution and this is the monotone solution, and for this part we have Crandall and Lyon's error estimate, so we can use that here. So for that we have this estimate, so I'm using this here, and here I have T epsilon. So if I choose my epsilon, this constant time is square root of delta x, then I can have square root of delta x everywhere, and then we derive the Crandall and Lyon's error estimate. Nice. And the second part. So in the second part, as in previous slide, I denote the consistency error estimate with this EJ. So that was the short form of the estimate. So we will get something like that. And in all these schemes, we have a CFL condition. So yeah, so again I am taking what I have to prove. So I have uj n plus 1 minus the exact solution. So I write down the scheme, and then I take the absolute value and the maximum. So I have this part and this consistency error estimate, it turns to that, then delta t times epsilon. So again if I do the recursion, here I will have 0, and here I will have total time, because I will have n here, then here I have the max of those things. And then again this so if we look at this delta t, because we have this CFL condition, delta t is the same order of delta x, so I can replace it by some constant time delta x. So I will have delta x here, and here if I choose my constant epsilon by constant time delta x, then I can have the same estimate here. So it's all dominated by delta x. So then I improve with the delta x. And similarly in the next part, so for high order, for staying in the high order, we want this quantity to be less than or equal to 1. So that means what we want, if I substitute the scheme here and use the definition of absolute value, then we end up with this epsilon value. So if we have this epsilon value, and then the scheme is the same as the high order scheme, and then it take the property that the total scheme is high order, and it's local high order. Okay, so it was easy to prove even the convergence results because the help of Crandall and Lyon's error estimate.
What do you mean by local high order?
Because the thing is, when you have the scheme, okay, yeah, so when you have the scheme, if you try to take the absolute value, this function is always bounded by 1.
Yeah. So what's the result in that case?
So in that case, because you cannot get the high order everywhere, it's just having locally.
How is that showing the estimate?
The estimate.
The result.
Now here I'm showing that error estimate for the filter scheme. Yeah, here
This is the consistency.
Yeah, the consistency. Yeah, we got the consistency estimate for here. No, not the estimate like I have before. It just says that the filter scheme is same as the high order scheme locally.
Consistency.
Consistency, yes. It's not like the error estimate for the other two cases.
I guess I'll ask if you have results that indicate that error is localized away from singularities or being polluted by the presence of singularities somewhere else.
No, it's just a consistency estimate because of the domination that the filter function always bounded by 1. So that term just disappear. You can't gain much from there. Yeah. Okay. Yes. Yes. So we have this consistency estimate here, and the scheme is locally high order because of that. Okay. Yes. So the scheme and for convergence, that part was enough. But numerically things are not working in that way. So this is something which we are doing numerically, but it's nothing to do with the convergence or whatever. So suppose we have this kind of Hamiltonian. It's a front propagation problem. So the problem is when you discretize and in the same shell you have change in speed. So for example, if this is my initial data, so what is happening in updated scheme, this front is going below to the minima from here, from the local minima. And similarly, if I have this initial data, so when this front move here, this goes above to the maxima. So only at those points, what I am doing, from the neighboring values, I am taking the minimum and the maximum. So this limiter correction is that in the neighboring points I am taking minimum if the scheme going below to the minima, and if it's going above to the minima, then I am taking the maximum minimum. Yes. So this is just to fix the numeric thing. Okay, and then this needed only in high order Hamiltonian. It's nothing to do with the monotone Hamiltonian. Okay. Okay. So for having the convergence results, we use epsilon to be less than some constant time of square root of delta x. So this is needed for converging towards the viscosity solution. And for having high order, so what we have for having high order, we want this quantity to be less than 1. So that means we want this to be less than 1. So if we replace this by a smooth enough function, some regular function, and then we use the Taylor series expansion, then we end up with the following estimate. So for having the convergence results, I need this upper bound for the epsilon, and for being in high order, I need this lower bound for the epsilon. So that's the only thing I could do for epsilon. I don't know how to tune this exactly, but I have these bounds. And in numerically, I used some constant time delta x, because the solution, the epsilon itself depends upon the second derivative of the solution. So you can update this value, and you can do online this value, calculate the second derivative and calculate the epsilon, but it's also working for some constant time delta x. And because of this epsilon monotone behavior, scheme is always going to be stable and nice. Okay. So here are some what I'm using for the numerical test. So I am using upwind scheme for the Hamilton-Jacobi equation. When I say SM, so I'm always using upwind scheme. For SA, I am using high order central finite difference derivative, just central finite difference. And when I combine these two, I use Runge-Kutta second order scheme to be in second order in time. And here is a small slide for the essentially non-oscillatory second order scheme known as ENO scheme. These schemes are the ideal of the scheme. Everybody compares everything with these schemes, but these scheme does not have any convergence or stability results, but they are high order and they are in the market from always, even before I born. Okay. So what these scheme does, so this is the form of the scheme. So for D minus and D plus, so it's second order because it uses the second order derivative. So you calculate the second order derivative and then you take the lower one, and then so this scheme is costly because every time you need to calculate this at every node, and then you write down the whole scheme. So okay, so this is just a simple form of the ENO scheme. Okay. So now what I'm going to do, I'm going to compare these schemes with the filter scheme. So here I'm solving this Econol equation in 1D. So I'll show you this data first. So this is my initial data. So when I'm using the central finite difference scheme, so we know it's unstable scheme is just blow up near the minima, and but filter scheme is doing quite well. Now we will go back and see the table. So here for the filter scheme I chose epsilon 5 times delta x, and so this filtration between the monotone scheme upwind and central finite difference scheme with Runge-Kutta in time, second order in time, and it's a central difference scheme with the Runge-Kutta second order in time, but it's unstable, and that's the Eno scheme, and filter scheme is doing better than Eno scheme. Okay, and next. So here I'm also solving this stationary problem, because with Obermann and Frosses and Obermann, they gave a filter function for this stationary problem. So for this problem I used both filter function, their filter function and mine, and the both tables are giving the same results. And so here if I use a central difference scheme, it's unstable, it's going nowhere, and if I filter them central difference scheme with the upwind scheme, it is high order, and the Eno alone is something, it's not very good, but it's okay. And when I instead of using central difference scheme, if I use Eno scheme and filter with upwind scheme, then it gives a better result. Okay, and these are the global error for this table. Okay. So now here I am solving this obstacle problem. So here, because you don't need to have Hamiltonian to be convex, so the scheme should work for this case as well. So first I'll show you the picture. So this is my initial data, this blue one, and this is my obstacle. So when time passes, because it's advection plus obstacle, and then it's go further, and it's time t equal to 0.3, and then so you see here there is you cannot have high order in these part, neither there and neither there, because they are not smooth. Okay, so that's why these error are local error. So what I did in calculating the error, I removed these parts, and then I just removed those points from the domain, and then I calculated the errors. So here again epsilon is 5 delta x, and so this was the advection plus obstacle, and so filter scheme is high order, second order, nice, and of course central difference scheme is unstable, and Eno is also high order, but you pay less computational time for the filter scheme. Okay, so now we will solve some 2D problem. So this is the rotation problem. So sorry. So you have this cone, and it's rotating. So in rotation I have the rotation with pi by 2. Okay, so that's the initial data. So in 2D, so just to note that in all these schemes, the filter scheme, I added the limiter correction. So every time I am taking the minimum or maximum when solution goes below to the iterative scheme. Okay, so here like in 1D I just have to take the minimum and maximum between 3 values, but in 2D they are the 5 values. So I am taking them in between the 5 values. So here I use epsilon to be 20 delta x, and so this is the first time when I saw central difference stable. So if I run for the next iteration, it's blow up, but for the low CFL number, it's a little bit stable. So at least filter is not doing anything wrong. So that shows that. Okay, so that's the picture. It's a nice rotation. Okay, and then this is the next problem where we have 2 front. This is the initial data. We have 2 front, and they are expanding and merging. So when they merge, So then you can have some non-smoothness when they merge to each other. Okay, so here I also choose epsilon to be 20 delta x, and that's the central difference scheme, ENO2 and filter scheme. Filter scheme is doing well, and if I use any other scheme, you cannot see the nice merging. Even it's really bad when they merge to each other. Okay, and the filter scheme is high order. Okay, so then I repeated the same test for 3D. So in 3D, so here I have 5 front. So on all these 5 front are expanding and merging together. So they are, so again when they merge, so there is this stripe everywhere of where the function solution is not smooth, then you cannot have high order. So if I write down the total error, it goes to the low order. But if I remove these stripes from everywhere, then the scheme gives the high order result, and that makes sense because you cannot have high order there. So here's the table. So yeah, this time I also decided to write down the CPU time because all those tests were fast, so they just run immediately. But now here we can see how much we are gaining with the CPU time. So in the filter scheme, the same thing. We have upwind scheme. Here actually we use Lex-Frederick flux for writing the scheme in 3D, and then we have central finite difference scheme and filter together with the limiter correction, and then we can have high order here. Central difference scheme is not converging. ENO is high order, it should be ENO2 is high order, but in computational time filter scheme is much more faster than ENO scheme. In ENO you need to calculate the second derivative at every node, then you need to compare them every time, and then filter is much more faster than ENO. Okay, so these are the nice numerical evidence. I do have some tests for the third order scheme, and they are high order, they are third order and faster, and okay. Okay, yeah, then I also put here, what did I do? Oh, this shouldn't be here. Okay, so in conclusion, what I gave, so I presented a very simple form of filter scheme, which is a combination of monotone scheme and a high order scheme, and then we have Crandall and Lyon's error estimate totally, and locally scheme is high order, and in those numerical tests, when the solution is smooth, the scheme is second order. And then the interesting thing is, for ENO scheme there is no convergence results available, but if in the construction of the filter scheme, if you replace high order scheme with the ENO scheme, then you can get the same Crandall and Lyon's kind of error estimate, because that epsilon function, those things bounded by 1, so it's just always bounded by 1. So whatever high order scheme you use, you can have that error estimate. Okay, and then we also so actually the example 2D and 3D, they are the problems coming from front propagation. So I had many tests when I tried to use the filter scheme for different kind of front which are not smooth, but after some time they become smooth. Like if you have a square and if it's expanding, so after some time a square become a circle, and the scheme is high order that time. Before it's low order, but then it's high order. And then we also have a error estimate for a stationary equation. So before I thought of putting it, but I thought I will run out of time, but it's not. So I didn't write it here, but you can prove the error estimate for this steady Hamilton-Jacobi equation, and then you need to use some comparison principle there. Okay, and then so here we use mainly central difference scheme with the upwind scheme, but there are several different kind of filtering possible. You can use any other scheme. For example, you can filter semi-Lagrangian first order with P1 interpolation with semi-Lagrangian high order schemes. And so the problem is with the epsilon, because for epsilon I was able to find the lower and upper bound only, but I exactly don't know how to tune this epsilon, and this epsilon is of course can be adaptive at every time step, so it depends upon the delta t and delta x both. And then the another thing, I would like to couple the discontinuous Galerkin method with the filter scheme, so hopefully it will give something nice. And so there are different coupling possible. That was the one kind which I showed you today. And so these are the references. So this is the paper by Crandall and Lyons, where they presented the scheme, first order monotone scheme for Hamilton-Jacobi equation, time dependent. And then this is a paper where Barl and Suganadis developed the theory for convergence of epsilon monotone scheme. And here's whatever I presented is coming from this paper and these papers. And yes, thank you.
Are there any questions? In that case, I'll ask one. So for viscosity solutions, you typically have the maximum principle, and will your scheme preserve that in
Yes, we have comparison principle, and the scheme preserve that. Even for proving this estimate, the estimate for the steady equation, you use that there. Yes, the scheme preserve that. Yes.
And in a couple of slides you gave L2 error estimates rather than L infinity. Is there?
Yeah, it was just a choice. They were just similar. So yeah, they were just similar. It was just a choice to put L2 error. Yeah. The only thing so sometime I give the global error, sometime I give the local error. That's where I'm cheating a little bit, because the globally, if solution has some kink, you cannot have high order. So I just remove those kink from the domain of calculation for error, and then I write down the tables. So sometime errors are local and otherwise they are global. Yeah.
But if you've got a local error concentrated on a lower dimensional set,
yeah.
would the L2
I think they were similar.
Okay.
Yeah, I think they were similar, quite close. Yeah. Yes.
I have a question. So let me understand. In your theorem, you say that you have higher order convergence committed to the solutions to be regular.
Yes,
right?
if the solution is regular.
So this is like a kind of consistency, right? You are saying if everything is very regular.
Yes, yes.
But is there any results telling you that the solutions are that regular, or is just the numerical evidences?
So you are what you are saying, the last line?
I'm saying that the theorem says that the solution must be regular.
Yes.
What are your evidences that the solutions are indeed regular, right?
Okay.
The theoretical solutions.
Okay,
right?
theoretical solution. That's the thing. The numerically we see this is high order, but the problem with this scheme, not the problem, but so with this scheme, whatever I try to prove theoretically, because this filter function is bounded by 1. So when you take the absolute value, whatever inside is just bounded by 1. So I cannot prove it theoretically to be high order, and it's like an open question from years. So there is no error estimate for the high order convergence. So here I can have numerically, but still there is, at least we can have Crandall and Lyons error estimate. But whatever error schemes available in the market, they don't have nothing. I mean, they just have nothing.
Because Crandall and Lyons, they don't depend on the regularity.
Yes. A strong thing. And it's like an open question. If anybody can improve, the Hamilton-Jacobi people will be so happy. Yeah. Yeah.
Okay, in that case, let's thank the speaker again.